This is the program running that robot. But it doesn't look like a typical piece of code because these are neurons, and they work more like your brain than your computer. I got my hands on SpikerBot, the new robot from Backyard Brains that teaches neuroscience by letting you wire up spiking neural networks and watch them control a physical machine. It has a slew of sensors and outputs meant to mimic creatures in nature, including a camera that can detect colors and a bunch of different objects. I sat down with Alex Hatch, the hardware designer who built it. At the end, I'll show you how I used Tinkercad and Alex's 3D templates for SpikerBot to build a custom accessory, a little plow that redirects the laser distance sensor towards the floor, so the robot can sense the edge of a table and stop itself from driving off. SpikerBot is the product of years of grant-funded research, including work from the original inventor, Christopher Harris, who brought the idea to Backyard Brains and co-wrote a grant to make it real. By the time Alex joined the project, there was already a very large, complicated robot to work with.
But where we started was like a big guy, So we used like these huge lithium-ion battery cages, like 18650 cells. We had some more integrated camera controller and all these things. And so I had some previous experience working at Ford in their battery lab. And so I've dealt with batteries a lot. If we're going to use lithium ion, there's a lot of countries that are just gone. Like we can't ship anything to Germany. There's all these additional regulations. And knowing what I know about that industry, like I'm just not the biggest fan of unnecessary lithium use.
Alex took on the mission to miniaturize the project so it would be accessible to more than just research labs.
So the humble AA battery, I think, has fallen out of style, but I think it's actually a great platform for a lot of reasons. I have nickel metal hydride batteries that I've had for like 12 plus years. I still cycle them through remotes. That's like the end of life. You know what I mean? Is when you just need that little pulse of electricity. But like you can use these for such a long period of time in like 20 plus devices. So like that is a good implemented battery technology because we haven't solved batteries as a whole yet. That was my first goal, was basically to get this whole giant thing and make it battery powered off of 4 AA's or as few as I could do. When I first came in, that was like the exercise was to miniaturize everything. And so the two big ones was moving over to the ESP32 platform. We grabbed some like cheapy ESP32 cam modules. And I wanted to see also what options there were for motors. I ended up settling on just continuous rotation servo motors, just because, you know, in theory, you could just swap that for another servo type and really flexible. They're really easy to come by. You can't be necessarily as like the trim kind of stinks where like rotating it clockwise versus counterclockwise in two different motors might get different speeds. But in our platform, that doesn't really entirely matter. And actually these little like glitches and errors contribute to the understanding of the brain because like my left bicep and my right bicep are not perfectly equally as strong, right? And so the brain is constantly compensating. And so we thought this would be a cool exercise anyways to like, you know, be able to put something in there that has to be fine-tuned, but is easily replaceable, easily commoditized. The surprise was that like you could run a lot off of 4 AA batteries. Your current budget is quite high, even with all of your stuff. We only have 4 LEDs, but they get pretty bright. You know, we've got a camera. We're hosting a Wi-Fi connection. We have now 2 motors. We've got a microphone, accelerometer. We've got a distance sensor. All the MEMS stuff, super low power. It's almost free.
Every sensor on SpikerBot is there for a reason, and the reason is always biology.
The camera is super critical because some of the first, you know, important things we learn about neuroscience is sight. And it's also one of the earlier things to evolve is like being able to navigation and differentiate left between right. I have to turn. And a lot of that's done with vision or these like external reaching sensors. A microphone is also one of those things. The auditory system is very sort of lo-fi in the brain, and so that's a really good sensor to interact with. Motors, obviously, we need to do something to move. The lights act like almost chromatophores in a color-changing squid or like a chameleon. Cells that will like kind of bloom when they activate and then slowly decay out.
And the accelerometer.
So the 3 bits of information that I'll have access are like if you tap the robot, so it knows if it's bumped. It'll know if it's on level ground or if you've tilted it or picked it up. And then the last one is just like a perception of, am I accelerating or not? Am I moving or not? So basically, like, if I try to back up and I hit a wall and I'm not moving, then it has a sense beyond the distance sensor that it's not actually moving. It's sort of a crazy thing, though, because our inner ear is like, there's these small crystals in a sludge, basically, right? And so it's like we're growing little crystals we got rocks in our head to help us figure out where we are.
And tiny hairs.
Yeah, tiny hairs and rocks.
It's all just tiny hairs and rocks up in here. Here's the thing. A meat brain processes information fundamentally differently from how we usually write code for computers. SpikerBot makes neurologic computing visible in a way that I haven't seen before. I asked Alex about his challenges with the project.
Part of it is like on the software side and stuff too, and just making sure that that's all happy, and that's a constantly iterated thing. But on the actual hardware, I would say a couple things actually were just like pitch points. One is just a little variance of ESP32 chips over the years, along with the variance of cameras, because there's ones that have the same chip, and technically, a lot of them get discontinued. And so there's just all this like juggling between little protocol things and, just things being updated. I've been working on this for more than 4 years, right? And so you have a piece of hardware, it works, you're really, really happy. You cruise on the software and the firmware, and you're all looking good. And then you go to make a newer prototype to integrate some things, and parts are out of stock, and the parts have changed. I think that's the part that's like really interesting. The idea of neurorobotics has existed since, I think, the late 50s, basically since analog electronics were, available enough to be able to tinker with. And the whole concept, starting up was basically making machines that are more responding to really simple, like, sensor input-output. So as, there's the classic Breitenberg vehicle, which is like one of the first simplest example in the app, where you have two neurons, one responding to like left field of vision, one in the right, and those directly will drive a motor, push it left or push it right, so it can track an object. And so this was done a long time ago. But what's really interesting to me that this serves, and I think there's been other spiking neural networks, but certainly nothing integrated and like ready for the public, back with a bunch of like real neuroscience stuff in there too. What's interesting though is that things that we take for granted as people, and you start coding, and it takes a lot of effort, like tracking an object. I mean, that two neuron vehicle, what's interesting about that is it's two neurons. Like, you can't make two lines of code do the same thing. Like, you're going to need libraries, you're going to need all these extensions and all this stuff, and it's just a slog. But then when you get into complicated, you do the opposite thing. Like, if I need a robot with neurons to count, that's not something you can do with two neurons. And so, like, math is really hard for humans. Computer is good at that. And SpikerBot working more like us is interesting because you see that reflected in like how many neurons and how complicated your circuits are. I've got a brain that can track a person and even back up when it gets too close. That's 3 neurons. And when you press play on that thing, it looks like a creature that's responding, and it's playful, and it's very organic because it's this twitchy, spiky thing, and our muscles twitch and all that stuff. And then I have a brain in there that is like, I think 30 neurons or so, that can count in binary to the number 3. So 0, 1, 2, 3. And it takes 30 neurons and this hyper-specific tuned, everything's got a really responsible role. And it's like, that's one line of code. You know, like 2 lines if you wanted to like reset it once to roll over. But that's completely different operation for a brain to do. And I think that that's like supremely useful. As these languages get more crazy, as like AI replaces people in coding, learning about the brain is still useful. Learning about the brain for like understanding our peers and ourselves is really important, I think.
SpikerBot has been in development for years, including peer review and classroom testing. Alex is pretty clear that the history is what makes SpikerBot more than a toy.
The more playful we make it, it still has to apply and be accurate to the science. We're using this model that was developed, I believe, in the early 2000s, called the Isaacevich Integrate and Fire model. And so this is like a computational model that was developed like for research purposes to replicate the different patterns that you would see if you recorded from cortical cell neurons inside of a living brain. And so the patterns that this model can produce are very similar.
Alex has been building SpikerBot for 4+ years. I asked him about his parts pipeline and if he shops at DigiKey, this video's sponsor.
DigiKey has been my go-to, actually, because, I don't know, just doing projects over the years, their search is really efficient. I can almost find everything that I need. If I've got to actually build, like, the actual PCB, like, usually if I can find about 90% plus of what I need to find in DigiKey. And it's fast as heck. You know, it's like being able to get stencils really cheap too. All of those things make it a lot easier to go to like a big supplier like DigiKey, because these are going to be the same parts that I can use in production and the same formatting, and everything transfers over really easily. So we actually had a huge problem with 2 or 3 years ago. We needed to build 10 to 20 prototypes, and then a part would be out of stock, and we have a workshop next week. And so we've had those orders of, especially when we were using the ESP32 cam modules. It's got ESP, and it's got a little camera on there, and they're supposed to be the same. Some cameras would actually have the image rotated 90 degrees, physically look identical. I would say about half of the ESP32s, no matter what you did, couldn't get to flash. And so there was a lot of counterfeit problems. And whenever we've got things from DigiKey directly, there's really none of that insecurity.
So SpikerBot has a lot of great sensors, but the distance sensor faces forward. That's great for detecting walls and things in its path, but it has absolutely no idea if the floor is about to run out from under it. When I asked Alex about this during our conversation, he suggested mounting a mirror to the front of the robot at an angle to deflect the sensor beam downwards, so it reads the floor in front of itself. Alex shared the 3D templates he made for SpikerBot's Snap Fit accessories, which are designed to plug into the slots on the enclosure. The templates give you the geometry of the clip, so anything you build off of them just snaps right in. I imported the templates into Tinkercad, which is my 3D modeling software of choice because it's free and extremely easy to use. I needed a flat platform angled to hold a small mirror at about a 45-degree angle between the sensor and the floor. I was looking at my test print on the SpikerBot, and I thought it looked like a snowplow, so I leaned into it. I added a curved scoop front face, and now it's a little bulldozer that can clean off my table. Now all that's left to do is cut the mirror to size. Easy, I thought, as I ordered a new set of glass cutting tools. I hadn't done stained glass since I was a kid, but I had the sense memory of it, so for some reason I didn't feel the need to refresh my knowledge before diving in. That was a big mistake, and I broke a few mirrors before my hubris caught up with me. Broken glass everywhere. So, to cut glass quickly and easily, work on a soft surface and score the surface exactly once, using a straight edge as your guide and a specialty glass scoring tool. Then move the workpiece to the edge of the table so the score line is aligned with it, and with one swift motion, snap the glass down over the edge of the table. Even still, it came out a little jagged, so I used my tiny belt sander to clean up the edges. I attached the mirror to the 3D print with hot glue. You could also use double-sided tape. Next, it's time to make the robot use its new accessory. SpikerBot comes with a library of sample neural circuits, what they call brains, that you can load, modify, and save as your own. There's one called Explore, which is a great starting point for what I'm trying to do. The Explore brain does a few things. It randomly wanders around, and when the distance sensor reads below a certain threshold, meaning something is close, it triggers a backup response. The robot retreats, makes a sound, and lights up red, then goes back to wandering. The key to making this work to sense the floor is that threshold value. In the default Explore brain, it's set to trigger when something is close. I want it to react when something is far, signaling that the floor has disappeared. In the app, there's a range selector. I inverted the threshold. The floor should always be close, and when it suddenly reads far, that means you're about to go over the edge. And it works. Watch. it's not perfect. The Explore brain has some movement patterns that work fine on the floor, but are problematic on the edge of a surface. It can still back off an edge since it can only see in front of it, and if it's driving at too steep of an angle to the edge, it can slide off the side before the sensor sees far enough ahead to react. Alex also mentioned that since the bot is listening to the app, Wi-Fi congestion could slow down SpikerBot's response time, and I do live in a congested Wi-Fi place. So if I were to take this further, I'd tweak the movement settings to try to overcome the remaining issues. And there are so many other fun things to try with SpikerBot, I'm excited to continue exploring. See you next time. This video was made with support from my sponsors and donations from viewers like you through Patreon and YouTube memberships.